Good evening, everybody. What is crappening? Welcome to Tibbetts Physics. Today we are going to learn about parallel circuits. Parallel circuits have multiple paths for the current to flow through. There's multiple ways of drawing parallel circuits. So I'm going to show you one of them, which gives us a better idea of how the potential difference works and the definition of a parallel circuit. What we're going to do is draw a parallel circuit that has multiple branches, all stemming from the same wire. So they're going to branch off into three different locations, and they're going to recombine to the same wire, then back to the battery. Now the other circuit we could do is we could make it so they look parallel to each other. They're the exact same circuits, but they do look different. And as we can see in this one, the resistors are all parallel to one another. So one thing that we can notice off the bat is for a parallel circuit, there's different branches for the current. So if we label this resistor 1, resistor 2, resistor 3, we can see that the current that flows through resistor 1 follows this pathway. The current that flows through resistor 2 follows this path, and the current that flows through resistor 3 follows that path. If we wanted to place an ammeter to measure the current that flows through R1, we could either place it right after R1 or right before. If we want to measure the current that flows through R3, same thing, right after or right before. But if we want to measure the current that flows through R2 and R3, we'd have to put it after R1, but before it splits off into two separate branches. Or we could put it where they combine, so the current flowing through R3 and the current flowing through R1 are going to recombine at that ammeter. And what we can tell is because each current has their individual paths, that the current flowing through each resistor will be different, and they're all going to recombine before they reach the battery or after they exit the battery. And we can see that the total current is the sum of each individual currents. If we look on the circuit on the left side, we can see that the potential difference is going to be the same starting and ending spot for each resistor, and that tells us that the potential difference is going to be the same through R1, R2, and R3, which also means it's going to be the same through the battery. So what we could say first is that the potential difference of the battery is the same potential difference that goes through R1, R2, R3, and so on. We also saw that the total current is the sum of the current that goes through each branch. So I total is I1 plus I2 plus I3 plus ... Notice that these two are the opposite of series circuits. So for a series circuit, the current is equal across each resistor, and the potential difference is the sum of all the individual resistors. Now what we last want to figure out is how to calculate the equivalent resistance of a parallel circuit. What we're going to do to calculate the equivalent resistance is utilize Ohm's law. And if we look at the total current, that would be the total potential difference over the equivalent resistance. And we know that the potential difference is the same across each resistor, and the currents add up. So we can also say V total over Req is I1 plus I2 plus I3. If we utilize Ohm's law for each individual resistor, we'll have V total over Req is equal to V1 over V1 over R1 plus V2 over R2 plus V3 over R3. all the potential differences are the same across each individual resistor. So if we pulled out the potential difference and divided by both sides, all the V's will go away, and that's going to leave us with 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus ... If we were to calculate this in our calculators, what I'd recommend doing is calculating the right-hand side of the equation. So add up all of your individual resistors, 1 over the individual resistors, keep it as a fraction, and then 1 over keep it as a fraction, and Req is going to equal the inverse of the sums of your individual resistors. So inverse of 1 over R1 plus 1 over R2 plus 1 over R3 plus ... So let's say you add up all your individual resistors, and you're left with 1 over Req is equal to 7 over 10 ohms. 7 over 10 ohms. To get Req, all you have to do is take the inverse, which would give you 10 ohms over 7, or 10/7 ohms. What's interesting about a parallel circuit is if we go back up and look at our parallel diagram, we know that if we were to add another branch, so if we're going to add another branch, a 4th resistor, what we're doing is we're adding more current. So the sum of the currents is now going to equal I1 plus I2 plus I3 plus I4. So as we add more branches in parallel, the total current is going to increase. So I total is going to increase. Now at the same time, when we add more branches, we know that the potential difference across each resistor is equal, and we also know that it equals the potential difference across the battery. So as we add more branches, the potential difference stays the same. As a consequence, as we look at Ohm's law, I equals V over R, and we'll solve for R. So R is equal to V over I. We could see that if V stays the same and I goes up, as we add more branches, the equivalent resistance goes down, which goes against our intuition, but we could see that the current is increasing with a constant potential difference, which means R has to go down. Now also, if we look at our parallel circuits, let's just add one more for the sake of looking at what happens. If we want to look at the brightness of the bulbs, when we add another branch, so now we have a 5th one, the current that goes through the 4th, 3rd, 2nd, and 1st stays the same. The potential difference that goes through each individual resistor stays the same. So as we add or subtract branches, because I stays the same through each individual branch, and V stays the same, we can say that the brightness of each individual bulb remains the same as well. Remains the same. However, because now we have more light bulbs, we say that the total brightness of the circuit will increase. So total brightness increases. And as we saw from the previous video, this is a result of the power is increasing. So just to reiterate, as we add more branches in parallel, what happens for each individual branch remains the same in terms of their brightness, their current and potential difference. But the total amount, if we combine all those light bulbs together, we'd get a much brighter light bulb. So the total stays, the individuals remain the same, but the total brightness and power increase. Okay, so why don't we look at practice problem number 11, where we have a parallel circuit with 3 resistors, and we'll analyze this one together. So number 11, we have 3 resistors in parallel. We're going to draw them as if they were parallel branches, but you could draw it however you want, as long as it's a correct representation. We've got an 18-volt battery. R1 is 3 ohms. R2 is 6 ohms. And R3 is 9 ohms. And like before like the last question, before we look at the questions, let's make a VERP diagram. Fill in everything that we can. So we just copy and paste your VERP. We'll fill in all the given information first. So we know each individual resistor, 3 ohms, 6 ohms, 9 ohms. And the equivalent the total potential difference is an 18-volt battery. So from here we've got a few options in terms of how we want to analyze this. Let's start with the easy math first. And we know the potential difference is the same across each resistor. So V total is equal to V1 equals V2 equals V3, which is 18 volts. So let's fill in 18 for all of our potential differences. Now we have a couple of options. We could either find the currents through R1, R2, and R3, or we could find the equivalent resistance. Let's find the currents first, and I'll show you multiple ways in which we can calculate the equivalent resistance. So step 2, we know from Ohm's law, let's look at I1. I1 is V1 over R1, which is 18 volts over 3 ohms, which gives us 6 amps. We can do the same thing for I2 and I3. We'll get 3 amps and 2 amps. And then we can use our knowledge of parallel circuits that the total current of the circuit is the sum of all the currents through the branches. So I total is I1 plus I2 plus I3. So if we add those all up, we get 11 amps. We'll put that in our chart as well. Okay, now we can see that we've got the equivalent resistance left to find. And we have a few ways of doing this. So I'll show you the easy way first. We could go back to Ohm's law. I is equal to V over R. If we isolate R, we get Req is equal to V total over I total. So that's 18 volts over 11 amps. And we do the math, and that gives us approximately 1.6 ohms. Now the other way we could do this is we could use the rules for parallel circuits, where 1 over Req is 1 over R1 plus 1 over R2 plus 1 over R3. So if we plug and chug, we get 1 over Req is 1 over 3 ohms plus 1 over 6 ohms plus 1 over 9 ohms. So we'll add those all up in our calculators, keep it as a fraction, and we do that, we get 1 over Req is equal to 11 over 18 ohms. So to get Req, all we do is take the inverse, which is 18 over 11 ohms, which gets us to 1.6 ohms. Okay, and then the last step for this question is to calculate the power. We could use any of the power formulas. In this case, I'll use P is equal to V times I. We'll show our work for the first one. So P1 is V1 I1. That gives us P1 is equal to 18 volts times 6 amps. That gives us a power of 108 watts. So 108 for the first one. And then we'll do the rest in our calculators. We get 54 for the second one, 36 for the third one, and 198 for the equivalent power. The fact that they're diminishing has nothing to do with the order of the resistors. It just has to do with the combination of the potential difference, the combination of the potential difference as well as the current through each of those individuals. And that's it for parallel circuits. Please like and subscribe if you found this useful, and I'll see you next time. See ya!